Okie dokie. I'm going to wrap up this section, picking up from how you can use this chart to help you with wordings of the final conclusion. So the non-statistical sounding conclusion. Starting out, just does the claim, like the original claim, have some condition of equality? Like say, for example, if our claim could be that the XOR method effectiveness is equal to 50%. Then if yes, then go from there to figure out, okay, did you reject H naught? If so, yes, then some good wording you can use kind of as a template and then just insert your context. Is there sufficient evidence to warrant rejection of the claim that the XOR is 50% effective? Then say we did not reject H naught, we failed to reject H naught. There is not sufficient evidence to warrant rejection of the claim that XOR was 50% effective, for example. Then say for instead that our original claim did not contain any condition of equality. So kind of like that previous problem, say the XOR was better than 50%, then so basically our original claim does not contain equality and becomes H1. So our claim was that XOR was better, and so that P being greater than H1, that was the P being greater than 50%, that became H1, and so that's why our original claim became the alternative hypothesis. So then from there, again, did you reject H naught? If yes, then the sample data supports the claim that XOR method was better. Because this is the only case where we're saying that the sample data does support the claim. Then we could also have where if we did not reject H naught in that case, then there is not sufficient sample evidence to support the claim that XOR method was better. So again, this is just a template you can use to kind of help yourself with the final conclusion. Notice a few just last little things, some cautions with hypothesis tests. Never conclude a hypothesis test with statement reject the null hypothesis or fail to reject the null hypothesis. So this is the statistical conclusion you'll have. Don't end it there. Go further to like the more less statistical sounding conclusions like those. Then just make sure to always make sense of those and put them in terms of the context, essentially. Now, as far as accept versus fail to reject, some texts use the phrasing accept the null hypothesis, but it's not always very good phrasing to use because it's not 100% accurate. And so we are not proving the null hypothesis at any point, we're just testing it. And so we fail to reject says more correctly that the available evidence is not strong enough to warrant rejection of the null hypothesis. So basically, we don't reject it, but doesn't look like we can completely discard it. Now, there are also types of errors that can occur with hypothesis tests. So this type 1 error was mentioned a little before. This is that alpha level. And so it's basically a probability or mistake of rejecting the null hypothesis when it is actually true. And so rejecting H naught when actually H naught is true. Just that's kind of like the probability of that happening. And again, that's still that alpha. And there's also a type 2 error, which is, and it's kind of more or less an opposite of that, is the mistake of failing to reject the null hypothesis when it is actually false. And so this is represented by the symbol beta sometimes. And yeah, again, just it's also a probability for type 2 error. The calculation to find this is can be complicated, so we won't be calculating type 2 errors. And as far as calculations for type 1 errors, this is usually something that's just kind of chosen most of the time, within reason. This is just a little table kind of outlining those. And so again, we could set up this table where, say, this is the true state of nature. So truly the null hypothesis is true. Then we decide to reject the null hypothesis. So that's a type 1 error, rejecting the null hypothesis when actually it's true. If you fail to reject the null hypothesis when actually it's true, great, no error has been made. If what you actually do is the null hypothesis is false, if that's what actually happens, but then you decide to reject the null hypothesis, again, all good, no mistake was made there. Now, if it turns out the null hypothesis was actually false, and then you fail to reject it, again, that's an type 2 error. So an example for those, like we could be using our same XOR method scenario here. Still have our same hypotheses, so null hypothesis just being that the proportion is equal to 50%, alternative hypothesis being the proportion is greater than 50%. So we're going to identify what the type 1 and type 2 errors are. Now, a wording of possible type 1 error, so again, mistake of rejecting the true null hypothesis could be we conclude the probability of having a girl is greater than 50% when in reality it is not, and that could indicate your data misled you. As for what a type 2 error would sound like, and that's failing to reject the null hypothesis when it's actually false, there is no evidence to conclude the probability of having a girl is greater than 50%. Data could mislead you, but in reality the probability is greater than 50%. Now, there are ways you can try and help control those two types of errors, mostly have to deal with the sample size. And so for any fixed alpha and an increase in sample size n will cause a decrease in that type 2 error. So like say we just leave our alpha at 0.05, for example, increase the sample size, then we can just know we'll be decreasing the type 2 error if we do that. Then for any fixed sample size n, a decrease in the alpha will cause an increase in the beta. So decrease in type 1 will result in an increase in type 2. And conversely, an increase in the type 1 error will cause a decrease in the type 2 error. Now to decrease both the type 1 and type 2 errors, we can just increase the sample size. I just want to summarize the steps of a hypothesis test because we kind of broke them up quite a bit throughout these videos. So first steps are just identify our claims to be tested, then identifying the alternative if the claim is false, so some kind of opposite claim. From those two claims, we determine which one becomes H0 and which one becomes the alternative hypothesis. From there, then we choose our significance level, so our alpha or type 1 error. We decide which distribution to use. Like so for the XOR method we were talking about, we use the Z distribution, which is what you'll use mostly for proportions. If you're talking about means with hypothesis tests, then you may be using the T distribution or the Z distribution. And if you're talking about standard deviations or variances, then you'll use the chi-square distribution. So next step is to find the test statistic and the p-value or the critical value or the actual confidence interval depending on which sort of method you're using. And from those you get to use the results to figure out in the next step if you either reject H0 or fail to reject H0. So it's kind of your statistical sounding conclusion. Then your last step is just to restate the conclusion or the decision in context with non-technical terms. So that's where you can use that chart that we started this video with to help you with those wording of the final conclusions. And then just wanted to rehash a couple of the big ideas here. And just being that, so hypothesis testing is based on the rare event rule. So you can go back and read over that if you'd like. Then null hypothesis usually involves equals of some sort, while the alternative hypothesis is some sort of not equal. So it could just be straight up not equal to, greater than, or less than. Then test statistics is basically, or are basically, what you get when you convert a sample statistic to a z, t, or chi-square score. And you can never actually prove or accept a null hypothesis. That's why we just say reject or fail to reject. So in conclusions, reject null or fail to reject null, but everything relates to testing the null hypothesis. Just kind of always keep in mind, that's always what you're testing in an actual hypothesis test. And there's two more here. So hypothesis testing is extremely important to inferential statistics and is kind of all about trying to find chances of something at least as extreme as some sample happening. So taking your sample statistic, changing it into a test statistic, so one of those types of scores, and that's where you get your conclusions from. Then last big idea, just your three methods, p-value, traditional, and confidence interval. But we'll focus mainly on just p-value and confidence interval, because traditional is just kind of an expansion of the p-value. Oh, sorry, p-value is an expansion of the traditional method, or an extension. Yeah, and in the confidence interval method, you use the sample statistic to construct a confidence interval and see if the claimed value fits in it. All right, and that's an introduction to hypothesis testing.